Hello everyone, welcome to a video on electric circuits. This is the second lesson in the GCSE physics playlist. Quite a lot to get through today as I'm showing you here. We're going to start off with circuit symbols, then we'll go over AC and DC, then we're going to go over conductors and insulators and sort of the differences between them. There's a lot of equations we'll be going through today. We're going to go over current equals charge over time. We'll then go over voltmeters and ammeters, then resistance equals voltage over current. Then we'll go over the IV graphs. We'll also talk about thermistors, LDRs, and diodes. Then we're going to go over the rules associated with current and voltage. Then the total resistance rules in series and parallel. Then voltage equals energy over charge. Power equals current times voltage. And then energy transfer equals power times time. So let's just jump straight into it. So starting off with circuit symbols and diagrams, this stuff is quite straightforward. The main thing is that wires are straight lines that will connect between these components, and just remember that to keep them straight, and then remember that the circuit must be closed. If it's not closed, then current can't pass through it. So these are all the components you have to know. A cell, basically just two lines. One's going to be bigger than the other one. The bigger line is the positive side of the cell, and then the smaller one is the negative side. A battery is basically the same thing. The only difference is you've got two sets of lines and then little lines that go in between. Switches, basically, this is where the wire can basically be disrupted. So you can, disconnect a wire if you want to. The way you indicate this is by putting two circles down on each side. And then if it's open, then it will be obviously not connected like this. If it's closed, then it'll be like this. A bulb is a big circle with an X going through it. A fuse is a rectangle that goes directly through the wire. It's important that this line goes over it. Otherwise, it'll look like a resistor, which is down there. LED, the way I remember this one is it's basically you get a circle. I then think of this as kind of like a video play button, and then the LED will then have two arrows coming off it. Sort of like, just imagine these arrows as being light. The LED is having light come off it. Then you've got resistor, which is a rectangle. It's different to the fuse in the fact that the line doesn't go through it. That's the important thing. Variable resistors, the exact same thing, but with an arrow, a diagonal one going through it. Then you've got an ammeter, which is a circle with an A in it. Voltmeter, circle with V in it. Them two are quite easy. A diode is the same as an LED without the arrows, so just a circle with that play button looking thing in it. LDR is basically a resistor. You then put a circle with it or around it, and then these arrows, which again represent light. And the important part is that the light is going towards the resistor, basically. Then you finish off with thermistor. Basically, just another resistor with sort of like a hockey stick going for it. So it's really important that we remember all these. The most important ones are obviously, your ammeter, your voltmeter, your cell, and your bulb. They're the most important ones. But these other ones, a one marker could come up and ask you for one of these. So that's really important. This is the sort of exam question where it'll be like, Daniel S creates a circuit containing a battery, switch, and a bulb. He connects them all in a single closed loop. So basically, what I've done, you put your bulb down, you'll then have your battery. It doesn't really matter which way you have the positive one at, that doesn't really matter. And then a switch. To be fair, the switch could have been closed or open. I just had it open in this case, but that's kind of what any circuit diagram will look like if you get a question on it, so that's 3 marks. So then there's alternating and direct current. So there's two types of electric supply. You've got AC and DC. Now, AC is what the UK main supply is. So, the electricity that comes through your plug sockets and wires and stuff like that. The important part about it is that the current keeps changing direction. And this is produced by what we call alternate voltage. Basically, the positive and negative ends will keep on switching and alternating. Really important, the UK main supply is 230 volts and has a frequency of 50 hertz, that is. And cells and batteries are then the ones that supply DC. So, for example, if you've got, I don't know, a PlayStation controller, the battery that will charge that is a direct current. So yeah, the current flows in the same direction. That's produced by a direct voltage. So that's basically the difference between them two. Then we move on to conductors and insulators. So the difference between these is that conductors conduct electricity because their electrons are delocalized and can flow. So this is more of a chemistry sort of concept, but it's also really important in physics. And then an insulator is one where the electrons are fixed and therefore electricity can't flow through and it doesn't conduct it. Examples of each: conductors tend to be metals. So you've got copper, aluminum, silver, gold. Graphite, if you into chemistry, then that's quite an important one. Salt water as well. And then insulators, you've got stuff like rubber, glass, plastic, wood, ceramics, air. A good way of thinking about it is a wire is always made of like copper, so you have like a copper wire. It will then have an insulator around it. That's what the rubber around it will be. That's how a wire works, because obviously you don't want electricity going on the exterior of it. So then we move on to our first equation. Now, these equations for the most part are quite easy. The hardest part is just remembering the order of them. But yeah, so here we've got current equals charge over time. Electrical current is basically the flow of electric charge. Remember, it only flows if the circuit's closed, and there has to be a source of potential difference, i.e. a battery or a cell. The size of the current is the rate of flow of charge. So current equals charge over time. That is represented by I equals Q over T. The units is amperes equals coulombs per second. Just as an example here, let's say you have a battery and it passes a current of 2 amps through a cell over 2.5 hours. The way I would do this is I would do 2 amps equals charge over 2.5 times 60 times 60, which means that if you then rearrange that, you get Q equals 18,000 coulombs. So that's that equation there. Another sort of exam question we've got here. A current of 8 amps flows through a battery. Calculate in minutes how long the charger needs to be connected to the battery for 28,800 coulombs of charge to be transferred. So basically here we've got I equals Q over T. That can be rearranged to T equals Q over I. So then I do 28,800 divided by 8. I get 3,600 seconds. Remember, it has to be converted to minutes. So then to convert from seconds to minutes, I'm dividing by 60. That gives me 60 minutes. So that's how that works. All right. Now we have ammeters and voltmeters. So ammeters are the ones that measure the current in amps flowing through a wire. The important part is that it must be placed in series with whatever is being tested. So this is an example here where we're testing the current of this wire here. Notice how this is in series with it, and therefore it is measuring it basically. Voltmeters measure potential difference, which is in volts, across a wire. It must be placed in parallel with whatever is being tested. So for instance, here's our wire here. You can see that the voltmeter is in parallel with this wire. Let's say you were doing the potential difference of a cell. The cell would go here, and then the voltmeter would be around it. So that's basically the important part. It's just remembering the ammeter is current, and it's in series, and the voltmeter is potential difference in parallel. Then we get another equation. This is probably the most famous one. We've got resistance equals voltage over current. Remember, resistance is in ohms, and then voltage is obviously in volts, and current is in amperes. So ohms equals volts over amperes. So let's say you've got 4 ohms of 4 ohm resistor and a potential difference of 6 volts. That means we're going to do 4 ohms equals 6 volts over current. That means that current equals 1.5 amps. Another sort of exam question here. If we've got 2,300, a 230 volt source, which in this case would be the UK main supply most likely, and we want the resistance of 5 amps going through it. Well, V equals IR, so therefore R equals V over I. Therefore, we do 230 over 5 amps. That equals 46 ohms. So that's how that works. Right, IV graphs. So basically, the resistance of an ohmic conductor doesn't change. The resistance is always constant. That means that as you increase the current, the potential difference increases at a proportional rate. So it's called directly proportional. That means that if you plot what we call an IV graph, and keep in mind the resistors at a constant temperature as well, that means that basically it's a straight line that goes through the origin with a constant gradient, basically. A filament lamp is slightly different. What happens with a filament lamp is, as I put current through it, some of that current and the energy going through it gets converted into the thermal energy store. That's why, like, if you have a light, as it gets brighter, it also gets hotter because it's producing heat energy. Heat actually increases resistance, and therefore that means you get less current per unit of potential difference, because as I'm increasing the resistance, I'm also decreasing the current. That's why as potential difference increases with a filament lamp, the current doesn't increase at the same rate. We see we've got a bit of a curve starting here. So that's the two most important ones. There's also diodes, which we'll get onto now. Well, first of all, we'll do this as a question. So explain the shape of a filament lamp, IV characteristics for the quadrant where I and V are positive. So in that case, we're talking about this quadrant right here. So basically, as the current passing through the filament increases, the temperature of it increases. This causes an increase in resistance. This means less current can flow per unit of potential difference, hence the graph becomes shallower. That's the exact 3 marks that you'll get for that sort of question. Right, moving on to thermistors, LDRs, and diodes. So thermistors these are all resistors, and they all depend on different things. A thermistor depends on temperature. Now, this is really important. With the way these works, a high temperature equals low resistance, and a low temperature equals high resistance. That's sort of the rule that you've got to remember. Then you've got LDRs. They depend on light intensity. Keep in mind, bright light is going to be low resistance, and then darkness equals high resistance. Then you've got diodes. They depend on the direction of the current. So one direction will have very low resistance, and then the other direction will have very high resistance. So it only lets current flow in one direction. Now, I'm just going to show this as a bit of an example. Here we've got a thermistor, right? And here we've got a fan. Now, just to give this an example, if we were in a really hot room, then the fan is therefore going to start working. And the reason for that, the thermistor's resistance in a higher temperature goes down. That means that more current is going to pass through. Therefore, the fan has more current passing through it, and therefore, it works more energy is transferred. The room will then become colder. That's basically how that works. Now, something to keep in mind is that if you put the LDR, in this case, in parallel with the bulb, that means that it actually kind of has a reverse effect. So in this case, let's say we were in a really dark room. So a bright light means low resistance, but darkness means high resistance. That means there's going to be more resistance here with the LDR. And what that means is if there's more resistance here, that means that more current is going to pass through here and therefore go to the bulb. Therefore, in a dark room, the bulb lights up. So that's basically how that works. Just best way of thinking about it is just really look and think what is happening with the resistance. And then if you find out what's happening in the resistance, you then find out what's happening with the component. This is the sort of easy exam question. Just describe one everyday use for LDR and thermistor. LDR, lights can turn on when it gets dark. And then thermistor, heating turns on at a certain temperature. Or a fan, or a fridge, or anything like that, basically. Current and voltage rules are very important. In series, the current is the same throughout all the components, and it's decided by the total potential difference divided by the total resistance, basically. So that means that the current in that component equals the current in that component. It's all the same throughout. However, the voltage, on the other hand, is shared across the components. That means that the total potential difference equals the voltage of one component plus the voltage of another component, so on. More cells equals more total potential difference because it's cells that supply the potential difference. Now, parallel, it kind of switches over where current is now shared between the branches. So the total current equals the current of each individual branch added together. Remember that the current entering a branch will equal the current leaving it. And then with parallel, the voltage is the same across each branch. So the voltage in one branch equals the voltage in the other branch. So that's sort of the important rules there. Sort of an exam question here. Draw a circuit diagram for two filament lamps connected in parallel to a battery. Both lamps can be switched on and off without affecting each other. The important part about parallel is that, let's say I only wanted this lamp on. That means that I close this switch and then this switch remains open. That means that the current only passes through here and goes to this lamp, which means that overall, basically, I can determine which light stays on and off. That's why parallel circuits are used a lot more than series circuits, because it lets you use a lot more different things, basically. So that's how that works. Right, now, total resistance in series. The way you do this is the total resistance equals the resistance of the individual resistors added together, basically. So yeah, the two resistors share the total potential difference, and therefore the total resistance is just the resistors added together. If you then add another resistor, this increases the total resistance, and because more resistance means less current, the total current of the series circuit will then go down. Bigger resistors take a bigger share of the potential difference. That comes into more of an A-level thing called the potential divider, but in this case, that's just sort of a fact you need to know. So this is a good example. Here we've got a 2 ohm and 3 ohm resistor. That means that the total resistance is going to be 2 plus 3, which is 5. We then do 20 volts divided by 5 ohms. That means 4 amps is passing through this circuit, basically. Now, oh yeah, actually, here's another example. So here we've got 4, 5, 6. So we do 4 plus 5 plus 6 is 15. We then do 6 amps. No, sorry, 0.6 amps times by 15 ohms. That means we've got 9 volts passing through it. So again, we're just adding the resistance because it's in series. Parallel is a bit more confusing. So for two resistors in parallel, their total resistance is less than the resistance of the smaller resistor. This is probably one of the most difficult concepts at GCSE to grasp, but basically total resistance is smaller than the resistance of an individual resistor. And the way to explain this is this basically. So the resistors have the same potential difference at the source, but if you add more loops in the circuit, the current has more directions to go in. Therefore, the total current will increase, and hence the total resistance of the circuit decreases. Now, I've got a good full marker here to explain this. So this is basically asking, when we remove a resistor from a parallel circuit, what is going to happen to the total current and resistance. So the total current through the circuit decreases. This is because there's fewer paths for the current to take. Therefore, as a result of this, the total resistance of the circuit increases. Then mention the equation V equals IR. Decrease in current results in an increase in resistance, basically. That's your 4 marks there. Again, not an easy concept to grasp. Maybe look over that a few more times, but overall, that's just something that is kind of just a fact you've got to know. Then we move over to 3 equations to finish. So first of all, we've got voltage equals energy over charge. Basically, what this means is, as charge goes to the battery, it's the potential difference that supplies it with the energy. Energy is supplied at the power source. The charge then loses the energy as it's taken away by components such as resistors, right? So the formula is voltage equals energy over charge, which is volts equals joules per coulomb. Joules per coulomb is kind of another unit used for potential difference instead of volts a lot of the time. So a battery with a higher potential difference applies more energy for every coulomb of charge. So let's say you've got a 3-volt battery and 140 coulombs passes. The energy is going to be E equals QV, so 140 coulombs times by 3 volts equals 420 joules. Another sort of exam question, 200 volts, 10,000 coulombs. So that means we're going to use E equals QV again. So 10,000 times 200, that equals 2 million joules of energy transferred. Then we move on to another one. Power equals current times voltage. So this is another way of calculating power. So yeah, watts equals amperes times volts. Remember, power's in watts. So in this case, a 1,000-watt hairdryer has a 230 volt supply. Calculate the current. So in this case, I'm using P equals IV, which we can rearrange to be I equals P over V. So we're doing 1,000 watts divided by 230 volts. That equals 4.3 amps if I'm rounding to two significant figures. Then we move on to power equals I squared R. So power equals current squared times resistance. Basically, the way you get this is because V equals IR. If you substitute V for IR, you then get I squared R, if that makes sense. So yeah, basically watts equals amperes squared times ohms. I'm going to give an example of that now, sort of. So this is one where we've got 12 volts and 4 amps. So this is a more easy one where it's just P equals IV, so 12 volts times 4 amps. However, here we've got an appliance of 2,300 watts and a current of 10 amps calculated with resistance. So this is where R equals power divided by I squared. So in this case, we've got 2,300 divided by 10 squared amps, which equals 23 ohms. Right, final thing now. The energy transferred by a charge basically depends on how long and its power. So power is energy transferred per second. So energy transferred equals power times time. Joules equals watts per second in that case. So if you've got 600 watts and that's used for 5 minutes, how long would it take 750 watts to supply that? So first of all, E equals PT. That's going to be 600 volts times by 5 times 60 seconds. That equals 180,000 joules. If you then want to find out how long that would take 750 watts to do, you do T equals E over P. So 180,000 divided by 750 watts. That equals 240 divided by 60, which is 4 minutes basically is how that works. Final sort of exam questions to finish with. This should be in red. I do apologize for that, but 6,000 joules transferred in 30 seconds. Calculate its power. So that's going to be E equals PT, which is P equals E over T. So 6,000 joules divided by 30 seconds equals 200 watts. Calculate the difference in energy transferred by a 250 watt TV and a 375 watt TV if they're used for 2 hours. Basically, with this, you're just calculating the energy transferred with both. Then you do 2.7 million minus 1.8 million equals 900,000 joules difference. So that's all that. Big topic, but that's pretty much everything to do with electric circuits. There's a lot of equations to know with this, so definitely look over them. And yeah, if you did enjoy, please be sure to subscribe, leave it a like, and then yeah, comment down below any questions, and I'll see you later.